Good morning, everyone. Today we're going to continue our look at volumes of rotation over here, and now we get delicious cake. So continuing with the volumes of rotations, we're going to consider volumes of rotations when the axis of rotation is not the x-axis. We saw a little bit of that last time, but we're going to really hone in on that this time. And it's just a little bit of a tweak from the way we were doing this before. So the four-step plan is still going to hold true. We're going to locate the corners, the length of the radius, the area formula, and then integrate. But this time when we figure out the radius, we're going to have to really think about that. You know, it says here be very deliberate about the process. So the radius is the length from the curve to the axis. Okay, a lot of students make a mistake here if you don't reinforce that. It's always the curve to the axis of rotation. Okay, or the axis of rotation to the curve. In the case where the curve actually has a higher value, either below or above. If the axis of rotation is above their curve, then you would get a axis of rotation minus the function. But it's always the difference between a function and the axis of rotation. So over here, when we figure out this area, we've got the area bound by the lines y equals 1, which is this top curve right here. And the line x equals 2 is this line right here. And then the curve y equals the e to the negative x is this line right here. So this area that we're trying to rotate, it's already shaded for you, but you need to be able to locate that area, of course. So over here, the corners of the region have been labeled already. So the corners are always the intersection of two curves, so it's sufficient to solve an equation like f of x equals g of x. Notice also that the curve 2, e to the negative 2, has not been approximated to a decimal. Okay. No real need, since we're only really interested in the x coordinates, since we're revolving around a horizontal axis. Next we have the radius. So the radius is still a difference of y coordinates, but this time the axis of rotation is above the curve. So when that happens, we need to use the function r. The radius equals the axis of rotation minus our curve. So in this case, our r is equal to 1 minus e to the negative x. Okay, so now that we've got our radius, we're going to do our area formula. And again, since we're rotating, we know that the cross sections are going to be circular. So the area is pi r squared. We know r is 1 minus e to the negative x. And then finally, integration, we've got the volume equal to the integral from, well, I forgot the lower and the upper limit here. Let's see, the smallest value of x is 0, the biggest value of x is 2. So that tells me we're going to integrate from 0 to 2. And then we're ready to integrate. So the hint here is to expand the square. So let's take us up on that hint. And we'll go from 0 to 2. Expanding this, we've got 1 minus 2e to the negative x plus e to the negative 2x. Now we can just integrate each one of these separately. So the antiderivative of 1 is x. The antiderivative of negative 2e to the negative x is positive 2e to the negative x. And then the antiderivative of e to the negative 2x is negative 1/2 e to the negative 2x. You may want to slow that integration down if you're not as adept at this, but these are the antiderivatives. And then we're going to substitute. So pi multiplied by 2 plus 2 e to the negative 2 minus 1/2 e to the negative 4 minus pi, substitute as 0. That's 0 plus 2 times e to the 0 minus 1/2 e to the 0. Now be careful, because the second time you substitute a 0, or when you substitute a 0, you're not always assured that you're going to produce a 0 here. Putting those two together, we're going to get 2 plus 2 over e squared. That's that e to the negative 2 is over e squared. This is 1 over 2 e to the 4th. And then we're just going to combine these two together. So minus 2 and then plus 1/2. Putting everything to a common denominator, we've got 4e squared over e to the 4th. We've got minus 2 over 2e to the 4th. And we've got plus e to the 4 over 2e to the 4. And finally, in summary, we can say that we've got the volume of the solid is e to the 4th plus 4e squared minus 1 over 2e to the 4th. I saw a small error there, but that's been corrected now. So that is volumes of solids, disk method, if the axis of rotation is not the x-axis. So this moves us into our second skill for today, and that's going to be rotation about a vertical axis. So an additional step has to be taken, usually, not always, to transform all equations into functions of y, so f of y and g of y. But then the plan remains the same here, except for instead of a delta x, we're going to produce a delta y. So our integrals are going to be done in terms of dy. So let's just try this. Find the volume of the solid when the region bound by the lines, well, these are the same lines, right? 1, e to the negative x, and x equals 2 is rotated around the line x equals 2. Okay, so the region is actually the same region, but we're going to convert everything into terms of y. So this first function here, y equals negative x, that's going to turn into x equals negative natural log of y. Okay. So the corners are still the same, 0, 1, 2, 1, 2, e to the negative 1/2. And this time, e to the negative 1/2 is going to be important because that looks to be our smallest value of y. Now, the radius is going to be, I'm going to draw it over here because that might be easier to see. The radius is going to be the distance from the curve to the axis of rotation. That's going to be our radius. So the y-coordinate on the right side minus the y-coordinate on the left side. So on the right side, the x-coordinate on the right side minus the x-coordinate on the left side. So the x-coordinate on the right side is 2, and it's always going to be 2. And the x-coordinate on the left side is equal to negative natural log of y. So this makes our radius 2 plus the natural log of y. Notice that everything has to be in terms of y. And if you're a little fuzzy on that negative natural log of y, remember what we're saying here. The x-coordinate equals the negative natural log of the y-coordinate. So this is x on the right minus x on the left. Okay, we've got a radius, so the area formula works out kind of the same way. The area formula is going to be pi r squared, which is pi multiplied by 2 plus natural log of y whole thing squared. Same idea. We're going to integrate from e to the negative 2 to 1 and pi r squared. So let's write that all in there. We're integrating the integral from e to the negative 2 to 1 pi. Our radius is 2 plus natural log of y squared dy. Now this one says to use a calculator, and that's because integrating with our natural logs is a little bit funky here. We would have to integrate the natural log of, or the square of a natural log, which I don't think we really have time for. So let's go ahead and grab our calculator. We'll call up the integration function, and we're going from e to the negative 2 to 1, not 21, 1 pi, and then the quantity of 2 plus the natural log of, we're going to have to use, well, gosh, we could use y if we really wanted to. Natural log of y, and then we're going to square it, and we're going to do this in terms of dy. Sure, why not? Calculators now, you have the option of doing it this way. So let's integrate. Yeah, 5.432. 5.43284, and then, of course, a summary, which we didn't leave a box for, but let's go ahead and write that down. The volume of the solid is 5.43284 cubic units. So I hope you're seeing that, rotating around a vertical axis is really, the same process as rotating around a horizontal axis. It's just everything's in terms of y instead of in terms of x. So let's go with our important ideas for today. We have, when rotating about a vertical axis, the volume formula is from y minimum to y maximum pi y squared dy. And the radius in this case is either the function minus the axis or the axis minus the function. Okay. So that is our main idea here. Everything else is a little bit of a review. And I guess we should say that there's this idea of rotating about other axes. So it's always either the function minus the axis or the axis minus the function, regardless of whether it's a horizontal axis of rotation or a vertical axis of rotation. Okay, reading through this, and check your understanding, the word calculator jumps out at me. So we're going to use our calculator liberally here. We are to find the volume of the region bound by the curves y equals cosine x, y equals 1, and x equals pi over 2 is rotated around the line x equals pi over 2. So let's start by graphing this. In our y equals menu, we have cosine x and 1. Now there's no real way to, or no functionally good way of graphing x equals, I think it was 1. No, x equals pi over 2. So we'll have to just kind of draw that in. Okay, and let's go ahead and, we don't know where to start. I mean, I know where to start, but we're going to start with zoom 6, which is our standard. You probably could have started with zoom trig as well. In fact, I'm going to go ahead and go to zoom trig instead. Okay, zoom, and zoom trig is number 7, so we'll go ahead and do that. And the main difference here is that the tick marks on the horizontal axis are every pi over 2, I believe. Okay, so here is our curve, and we also need to do at pi over 2, which would be right about here. So let's zoom in there. In this case, I'm going to use zoom box because I'm not, I don't feel comfortable right now going ahead and picking those numbers, and this is just a quick way of doing it. So I'm going to go from push zoom box, and I'm going to cursor over from, in my case, the bottom left corner, and then I'm going to cursor over to the opposite diagonal corner, which is right over here, and try to make this look like the shape of the screen. And I'm going to push enter, and it's going to zoom only on the part where I have drawn a box. Looks pretty good. Okay, let's take this over to our work. It's really nice to be able to draw on the screen like this. So our region is also bound by the curve x equals pi over 2. And that was kind of the main reason why I went to the trig zoom. Ooh, this did not... I'll just shove this over. That's better. Yeah, the main reason I went to the trig view here is because I needed to figure out where pi over 2 is. And, of course, I probably could have estimated that using the graph, but I'm uncertain sometimes with some students are a little bit not as great with the trig as they could be. So that might help you a little bit. So here's our region. I've gone ahead and I've colored it yellow. We are rotating around the line x equals pi over 2. I kind of make a habit of making that red, but so we're rotating around this line right over here. Okay. That's our axis of rotation, and we'll draw our radius now. So our radius is that is not a straight line, is the distance between the axis of rotation and the edge of the curve. So that's our radius. So it's going to be a difference of x coordinates. So we need to know the x coordinate here and then the x coordinate there. Well, the x coordinate here is x equals pi over 2. But the x coordinate here, I only have y equals cosine x. So I know the y coordinate, but I don't know the x coordinate. So to go the other way around, we're going to go ahead and take an inverse cosine of both sides of this. And the inverse cosine of the cosine of x is equal to x. So we get x equals inverse cosine of y. And we can kind of see why this is a calculator question now. Okay, so the radius then is going to be equal to pi over 2 minus the inverse cosine of y. I forgot step 1. We were supposed to figure out the corners first. So let's figure out those corners. Over here, this is 0, 1. That's pretty easy to know. This one over here, that's pi over 2. And the cosine of pi over 2, which is 0. And up over here, that's pi over 2 and 1. So it looks as though my minimum value of y is 0, and my maximum value of y is 1. Great. So it looks like I have everything I need to do this problem. So now that I have the corners, I've got the radius. The next thing is the area formula. So the area formula is equal to pi r squared, which is pi multiplied by pi halves minus the inverse cosine of y, the whole thing squared. I've got the area formula done. well, this was step 1, this was step 2, this was step 3, and now our step 4 is just to integrate. Let's use a different color. Let's see, what nice colors can we use? Ooh, let's use purple. So we are going to integrate from a to b pi, oh no, I'm sorry, not pi, the area formula in terms of y dy. Okay, our lower limit is 0, our upper limit is 1. You know what? Let's color code that. 0 to 1. Our area formula is pi multiplied by pi halves minus inverse cosine of y squared, and then we are doing this in terms of dy. All right. Okay, we don't actually have to do any more than that because we're going to be doing this on our calculator. So let's grab our calculator now. From the home screen, we're going to call up our calculator, our integral, and we're going from, oh, I forgot, what is it, 0 to 1? Yeah, that was 0 to 1. Pi. And then our radius, pi halves, minus the inverse cosine. Inverse cosine is second cosine. Inverse cosine of y, and then dy. Oh, no, I forgot to square. That is totally my fault. Close off the parenthesis and then square. Yeah. That gives me a volume of, wait for it, 1.468. All right, the volume of the solid is 1.46838 cubic units. So that's it for the volumes of rotation for today, and we'll see you for more of this next time we meet for more calculus. See you then.